Okay, good morning. Let's start the class. So first of all, I hope that you enjoy the quiz. Yes. So, and today we are going to talk about a new topic. So this is called the Pigeonhole Principle, and this principle has also another name. So in U.S. or in the English-speaking zone, we call it Pigeonhole Principle. But in Germany or in France or in Turkey, so in some other places, this theorem or this theorem is also known as the Dirichlet drawer principle. So this is a mathematician who has used this kind of who has first used this kind of principle extensively in his work. So what is it about? So it is a very simple thing, but by using this, we can have some amazing results. So first of all, imagine you have a drawer. So let's say, so this is inside your house, and then in the first drawer there are socks. So they are colorful socks. So socks may be of, let's say, the following colors. It can be either a white one, or a black one, or a gray one. Okay. Now, so this is black, white, or gray. So somehow, in one night, you want to go out, and then you are about to pick some socks, to pick a pair of socks from the drawer to go out. But then suddenly, the electricity goes out, so it becomes total dark everywhere. But you are in a hurry. You have an important meeting, and then you have to wear some socks. Okay. So in that case, you can reach your drawer and pick out some socks from it, so that you may be able to take out some socks and then go out to find some place where you have light and then put the socks on. Okay, you are in a hurry. Okay, so what should you do? Okay, you don't want to choose the color anymore. As long as you get a pair of socks which are of the same color, you are okay. Okay, so you can pick one sock, two socks, three socks, and so on and so forth. So how many socks do you need to take so that you are guaranteed to get a pair of socks with the same color? So how many of them should we take? 4. Very good. 4. Why? Why 4? Why 4? Because with 4 socks, we must be able to find out a pair of socks with the same color. Is that okay? Okay, we will show that. So intuition, this is correct. With four pieces of socks, then there must be a pair. There must be 2 of them with the same color. Okay, we will formally show this is correct, but this is our usual practice, we know. Now similarly, so let's take a look. So this is pigeon, okay. And then let's say we have 10 pigeons. Okay, pigeons love to fly around, and then they have some duties. Maybe they are going to help us to send mail to our friend. Okay, so people who raises these pigeons will have prepared some place for them to rest. So these are the pigeonhole. Okay, it looks like some of your mailbox, right? In a big, yeah, in a big mansion. Okay, so we call this one the pigeonhole. Okay. So at night, okay, or in the evening, when they fly back, each pigeon will choose one of these holes to stay. Okay, we want to argue what? No matter how they are choosing the holes, there must be some hole. There must be at least one of the holes with 2 or more pigeons. Okay, so it can be, okay, so let me restate what I'm saying. Okay, so there can be a lot of different ways the pigeons can stay. Maybe all of these 10 pigeons are squeezing in this corner. Okay, this can be a possible case. Okay, and in this case, we can find a hole that has 2 or more pigeons. Is that okay? Or maybe it could be some case like 1 pigeon here, 2 pigeons here, 1, 1, 1, 1, 2, something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe It is like this. So there are 2 pigeons here, there are 0 pigeons here, and so on and so forth. And in this case, we can also find at least one of the hole, and then in this hole there are 2 or more pigeons. Is that okay? So no matter how these pigeons are choosing the holes, we can find at least one of them with 2 or more pigeons. Okay? Do you see any connections with this one and this one? This is the case where what? This is the case that you can imagine there are 3 holes. I just give it a name: a white hole, a black hole, and a gray hole. And then we are picking 4 socks in our example. So we can imagine that there are 4 socks, or each of these socks is a kind of a pigeon. So no matter how the pigeons are choosing the holes, we can find at least one of these holes with 2 or more pigeons. Is that okay? So in that case, we can find a pair of socks with the same color. Is that okay? Okay. So in general, we are saying something like this. Okay, so this is the theorem or the principle. So theorem, suppose that we have n plus 1 pigeons and n holes if there are n pigeons and n holes, and assume that each pigeon has to choose one of the hole, exactly one of the hole to stay, then at least we can find one of these holes will have, this has 2 or more pigeons. Is that okay? Okay. Now we can prove this. So this agrees with our understanding. So if we pick 4 socks, then, and there are only 3 colors, then 2 of them are of the same color. It can be the case that all of them are of the same color, but we are including this case here. There is 1 hole with at least 2 pigeons. Is that okay? Now the proof is, so we may try to argue this theorem like, okay, in the worst case, if every hole has 1 pigeon, then the last pigeon has to go into some hole. And in that case, there must be a hole with 2 pigeons. Is that okay? But this one, it is not that formal, not that rigorous. It is because you are talking about the case where all of the holes has 1, and then one of the hole will now have 2. You are not considering all the possible cases. There can be cases where all the pigeons go into the same hole, right? And in this case, it is also okay. So to argue this more formally, let us prove this by using indirect proof. So we are going to prove this by, let's say, proof by contraposition. Let's say by contraposition. So contraposition is what? So it is of this. So this statement, this theorem is of this form: P implies Q, right? So instead of proving P implies Q, we can prove it by not Q implies not P. Is it okay? Okay. So not P implies not Q. So not Q, what is it? So we are going to prove this by proving this directly, and we are going to use a direct proof to prove this part. So a direct proof to prove this part, we may assume not Q is true. So assume that not Q is true. So what is meant by not Q? Here, at least 1 hole has 2 plus pigeons. The negation of this will be what? Good. Assume that. Very good. No hole what? No hole has 2 plus pigeons. Okay, no hole, assume that no hole has, let me write it here. Assume that no hole has 2 plus pigeons. Is that okay? Assume that no hole has 2 plus pigeons. Then what? Then it means that every hole has 1 or fewer pigeon. Is that okay? Is that okay? So this implies what? So thus total number of pigeons so each hole has 1 or 0 pigeon, 1 or less, okay, 1 or fewer pigeon. So the total, there are n holes. So the total number of pigeon is less than or equal to n. Is that okay? So we get not p. So there are so it is not the case that there are n plus 1 pigeons. And done. Is that okay? So we start from not Q, no hole has 2 plus pigeon, and then in the end we get not P, so that it is not the case that there are n plus 1 pigeons, because we have less than or equal to n pigeons. If you are okay with this, could you please raise your hand? Okay, excellent. Okay, as a practice at home, okay, so I'm using proof by contraposition here. The same theorem can be proven by proof by contradiction. Okay, you can work it out and compare your proof with the one that is in these lecture notes. So in the lecture notes we are using proof by contradiction, but these two are the same. Okay. Now before we and this is the basic version of the Pigeonhole Principle. And there is a, let me use the board here, there is a generalized version of the Pigeonhole Principle. Generalized Pigeonhole Principle. Okay, so to prove that, so let me write down what it is here first. Okay, so there is the general version. This time we start with n pigeons. If there are n pigeons rather than n plus 1, if there are n pigeons and k holes, then at least one of them, one hole, has how many pigeons? Has n over k. I will explain this notation. This is called the ceiling function. N over k more pigeons. Okay, so there is a notation n divided by k and then this one. Okay, this is called the ceiling function. This is the smallest integer that is greater than or equal to the term inside. Okay, so let me explain it. So for instance, so this is called the ceiling function. Ceiling of x is defined to be the smallest integer with value more than or equal to x. Okay, so for instance 0.5 if you take the ceiling, it will be what? What is the smallest integer greater than or equal to 0.5? 1. Is that okay? Okay, and then 2.7. This will be equal to 3. Very good. 4. The number 4. What is the smallest integer that is greater than or equal to 4? 4. Very good. 4. Minus 2.3. What is the smallest integer that is greater than or equal to minus 2.3? Minus 2. Very good. Excellent. So it is minus 2. Okay. So in general, we must have this relationship. This x is the smallest integer greater than or equal to x. So it must be, so x will be smaller than or equal to this one. Is that okay? Let me save some space here. So here, so we must have x has to be smaller than or equal to this one. Is that okay? Is that okay? But then, if you so this is an integer. If you minus 1, this will be an integer that is smaller than it, right? And in that case, x will be strictly greater than this one. Is that okay? So the integer, the value of x is always between the ceiling of x and the ceiling of x minus 1. Is that okay? So this is called the ceiling function. So it is the ceiling, okay? So there is also an opposite of this one. So we can talk about something like this. So the above are ceiling, these are the ceiling functions, okay? So we can talk about something like this. So let's guess, what does it mean? It should return an integer that is what? The integer, the largest integer that is smaller than or equal to x. Is that okay? So this is the largest integer with value smaller than or equal to x. Is that okay? And then this has a name. Okay, let's guess. Okay, we call this the ceiling function, right? So how do we call this one? Okay, ceiling is this one, right? So the opposite is floor. Very good. So this is called the floor function. Okay. So again, the floor function, you have this one. So x will be greater than or equal to the floor of x, but then it will be strictly less than the floor of x plus 1. Is that okay? Okay? Is that okay? Okay, now we have this understanding. Let's take a look of the generalized pigeonhole principle. So it says that if there are n holes, and then if there are n pigeons and k holes, then one of them will have at least n over k ceiling or more pigeons. Why we call it the generalized version? Because if you know this result, you don't need to memorize this part. The reason is that if you put this as n plus 1 here, and you put this as n here, it is saying that at least one hole will have n plus 1 divided by n ceiling or more pigeons, right? So what is the value of this one? N plus 1 divided by n, and you take the ceiling. What is this? So you assume that n is at least 1, okay. So what is the value of this one? This is slightly more than 1, am I correct? But it cannot be greater than 2. So this one is always equal to 2. Is that okay? So this is the same as this one. Okay, if you put n to be n plus 1, if you put k to be n, then you can get the original, the basic version of this pigeonhole principle from this one. Okay? And then how do we prove this? The proof is again by contraposition or contradiction. Okay. So let's do the proof very quickly. So we are assuming that we are doing this by contraposition. So proof. So we assume what? We assume that no hole has this many pigeons. Is that okay? So that means what? So then each of these hole has, this is an integer, right? So if you do not have this many pigeons, then it has n divided by k minus 1 or fewer pigeons. Is that okay? Is that okay? So if you don't have this many pigeons, then you must have this one or fewer number of pigeons. Is that okay? Does that make sense? Okay? Yeah. So this plus or this minus may be a little bit confusing. If you cover this, if you don't have any hole with this one or more, then that means that every hole must have this one or fewer. Is that okay? Good. So total number of pigeons so the total number of pigeons must be what? Must be less than or equal to, how many holes are there? K times this one okay. But then this one, if you look at the result over there, x minus 1, x taking the ceiling, minus 1 must be strictly less than x. So it is strictly less than k times n over k. And k times n over k is equal to n. So we get the result here. So here, we count the total number of pigeons, and then we find out that it is strictly less than n pigeon. And then we are saying something that not p is true. It is not the case that we have n pigeons, because we are having strictly less than n pigeons. Is that okay? Okay.